Hello, this is the second video of the Build the Model section for the modeling process. In our last video, we went through some terminology associated with building a mathematical model. Here we're going to see that in action. And for our particular example, we're going to try to describe the height of a falling ball as a function of frame number. So I encourage you to pause the video, grab a ball, grab a meter stick, grab a friend and a recording device, and try to collect your own data. And then look at your video frame by frame and try to get some measurements. And it will be helpful to see if you can try to get a sense of what the measurement error is, because there might be a little bit of blurriness in your video, or maybe the meter stick might be hard to read, whatever you're using for a measuring tape. So if you have time and the resources, go ahead and do that right now. If you don't, then you're welcome to use the data I'm going to provide here next. To keep things simple, I'm just going to provide 3 frame numbers and 3 heights. And we're interested in frame 13, 16, and 19. And the heights corresponding to those frames are 5.1 feet, 4.9 feet, and 4.4 feet. And in terms of measurement error, the video is a little blurry, so these are all within plus or minus 0.2 feet. All right. Now, let's start with the data-driven approach first. By the way, we can ask ourselves, are these continuous variables, discrete variables? Notice the ball is changing, the height is changing continuously over time. But because we're doing it by frame number, it really is more of a discrete situation. However, because the ball is moving continuously, if we want to use a continuous function to describe the motion, we can. But if we found a discrete model that only worked in increments of frame numbers, that would be acceptable because that's the way the data was collected. So we have some flexibility there. Now, since it's a data-driven approach, we're going to just focus on the data. So let's plot the data. And again, you can do that on your own and pause the video and see what model you think fits. But I'm going to show you what I did here next. So here's a plot of the data. And notice if we're just kind of blindly looking at the data, not thinking theoretically, not using previous knowledge, we might look at this and see that it looks approximately linear. So we might try to guess a line that would go through this. Now, there's a couple ways we could do that. We could just try to eyeball a line with a ruler, right? Maybe we would try to split the difference between the data points, or maybe we would just connect 2 dots. If I was going to connect 2 dots, it seems like the first and third dot would be a better choice, but I might draw it a little bit off. Or I could just use the first and the third points. If we do that, we can use the point slope form of a line, where the slope, of course, is just the change in the height over the change in frame number. The change in height is a negative 0.7. Change in frame number is 6. And then the point, of course, is, we'll pick the first point, so t minus 13 plus 5.1. Okay? So that would be one model for this data. And if we want to see how that plays out, we could plot it. Now notice, since we're talking about frame numbers, instead of drawing a continuous line, I could, if I want, plot single dots to correspond to each value. And notice we could, if we wanted to, we could extrapolate and make predictions for earlier frame numbers or later frame numbers. We can also interpolate, since we're only given frames 13, 16, and 19, we could also make predictions for what happens in frames 14 and 15 and 17 and 18. One thing to be aware of is that there is definitely some error here. Now, is this formulation error or is this measurement error? We can't say for sure, because notice that difference is only about 0.1 feet. So that's within our measurement error. So it's possible that the true value actually is 4.8 and this line is perfect. But it's also possible this is formulation error and that my line will actually not be the best choice of a model. And that's where extrapolation can give us some insight if we can happen to look at our video and see what happened before or after. For example, I know from the video that 5.1 is about the maximum the ball achieves, maybe 5.2, somewhere around there. So to predict that it goes on forever would actually, in an increasing way backwards, would not be correct based on other information I have from the video. So that would be a concern I would have about this model. So that is the data-driven, a very simplistic data-driven approach. What about a theory-driven model? So in this case, we want to have some reason to expect a particular type of function without just plugging in numbers from our video. Now, you probably have seen this before, especially if you've had a calculus class. But one way of thinking about it is to say that, well, I know that the acceleration of the ball is based on gravity, the acceleration due to gravity. All right, so we're going to assume this. Notice this would actually be relevant if we had done the define the problem part of this modeling process first. Since we're focusing on building the model, we skip that stage, but if you had worked through that stage, you would have come up with some assumptions, and one of the assumptions most likely would be to ignore air resistance and to assume that the only force acting on the falling object is gravity. And if that is the case, then this is one of our big assumptions, which, if you know calculus, tells us that the second derivative of position, or in our case height, is acceleration. Now, the nice thing about this is once we have this, then we can integrate twice to solve for h. Now, I won't get into all the details, but if you do that integration twice, and we've seen this formula before, we get gravity divided by 2 times the time squared plus some initial velocity times time plus some initial height. And notice the nice thing about the theory-driven approach is that we have completely solved for a model and we haven't needed to use data for any reason. Now, this works best though if we know the initial velocity and the initial height. If I don't happen to know that, then I will have to go back to the data to solve for those values. So we're not going to get into those details, but I will say that if you solve for V naught and H naught, right, assuming I don't have any way of measuring that otherwise, then we get a formula of H of t is equal to negative 0.0167 t squared plus 0.4167 t plus 2.5. Notice another thing we would have to keep in mind is our time unit here is in frames, not seconds. So one thing we would have to be careful of is gravity is not the traditional either 9.8 meters per second squared or 32, right? Even though our height is in feet, our time is in frames. So that's why this number may look a bit unfamiliar. All right, so what does that look like? So if you plot that quadratic function with our data, notice we get an even better fit than the linear model. And notice we don't have to pick data-driven or theory-driven. We can pick the best of both worlds. And in this case, we can see that this is so far a better fit than what we found before. In fact, it also illustrates that I expect the height to top out here somewhere around 5 feet, a little over 5 feet, which from the video we know is true. All right. And then we can also extrapolate. And again, if we have the video at our disposal for future frames or earlier frames, we can see how accurate that extrapolation is. Now, if we wanted to calculate something like absolute or relative error, we certainly could. For instance, on our earlier page, when we noticed that we were off by 0.1 feet, right? That would be an absolute error, right? 4.9 versus 4.8. And if I wanted to calculate a relative error, I could do 0.1 divided by, again, we don't know what the actual is, but in this case, since we measure the 4.9, we might assume that that's the actual, and our model is predicting 4.8. And so we can say, all right, 0.1 divided by 4.9 is our relative error, and then we could work that out to get a percentage if we wanted to. But we might also be interested in how good of a model is this? How susceptible is this model to error that's in the measurement phase? All right. And so in that case, what if we adjust the value at frame 19? So what if we're not 100% sure that that value is correct? And so we come up with two alternative quadratic models. And that's what these graphs here show. So we're given the so-called true value is 4.4, but since we have a measurement error of 0.2 feet, what if we pick 4.2 or 4.6 as alternatives? Notice how much the quadratic would change based on that one value being different. So these two data points remain the same. The third data point changes. And notice, especially in terms of extrapolation, we get very different numbers. Interpolation-wise, especially between these two values, almost no difference. So it's good to be aware of when we're building our model how much error is in the output based on the error that is in the inputs. And this is an example that can be pretty dramatic if you extrapolate very far, which is why extrapolation is always a dangerous thing to do. So this is a simple example, and again, we have lots of different mathematics we can use to build models, but this gives you a little bit of an idea of how some of that terminology applies in this particular case. We'll see you in the next video.